Good morning, everybody. These are the ones that decided to come back even after yesterday. Congratulations on sticking with it and being stubborn. This next unit, okay, where we move into magnetism and all of its effects, right? Some people have been asking me. I think it's just as hard as the last unit. This class is really front-loaded on the difficulty. Electricity and magnetism are difficult concepts. The third unit is a lot easier. I always get told that by students, and I think it's true. And then the fourth unit is, I don't know, mixed bag. For some people it's easy, for other people it's hard, whatever, right? But certainly the difficulty is here in the first two units. And after that, we're going to get a little bit of a break. So keep holding on. You got this. You can do it, right? And come talk to me if you ever feel like you can't. Turn to your neighbor and tell them everything you know about magnets. Just go. Just kind of brainstorm a list, and then we'll talk about everything we know about magnets.
Do you remember those little egg-shaped magnets? Big black two put them together.
Oh right, yeah, that's cool.
Well, I know it's like.
I think they're not as fast for like the new TVs.
Not too sure. I want to find out.
Yeah, it's too expensive to test.
All right, what'd you come up with? What do we know about magnets? North and south poles, okay? So this sounds a little bit like what we talked about when it came to electric fields, doesn't it? And electric charges. So with electric charges, what are the two flavors? Positive and negative, right? So what's up with the whole north and south? And again, it's like another set of flavors, right? Why not just call them positive and negative? And I mean, we could argue that you could just label them whatever you want. But magnetic fields are distinct from electric fields. We're going to talk about those distinctions. We're going to borrow a lot of what we already understand and know about field theory from electricity. But the reason we talk about them differently is that they are unique from each other. So what else do we know about magnets? Are there any rules about like north and south? Okay, there's attraction and repulsion. So again, we're back to forces, aren't we? Okay, so we got to have sort of like I don't know if it's like a Coulomb's law version for magnetic fields. Maybe you can see the writing on the wall here where we're kind of going to go with this, right? So what are the rules? Like what happens when you try to get a north pole and north pole together? They repel each other. Right? So we're back to the rule of likes repel and opposites attract. Okay, did anybody, anything else about magnets or magnetic fields? Yeah.
I know you can rub a magnet on a needle.
Okay, right? We can take something that is not magnetic and turn it into something that is magnetic. This is, again, a little bit like kind of putting charge on stuff, right? But we really kind of have to figure out what makes these two things distinct. So, yeah, that's pretty good. Anything else? Magnets respond differently than electrical charges do, okay? Heating up a material that is magnetic will destroy its magnetism. There's other ways to go about doing that. You're going to discover some of that next week in lab. Not that we're going to heat anything up, but we're going to magnetize, demagnetize things. So I have in my hand a magnet, okay? And I've put an identical magnet on a little stand that can rotate, right? Okay, so this thing can kind of freely rotate. And if I disturb it, right, it will kind of, do you see how it kind of aligned itself? Right? So if I spin it again, Just stir a bit. Let's see if it goes to a random. Nope. Nope, definitely not doing a random thing, right? Okay, it's coming right back to its thing. I did my best to level this, right? So I'm pretty sure this thing is free to spin regardless, right, where it goes. But this magnet wants to align itself with something else. What's it aligning itself with? The magnetic field of the Earth. We never talked about the electric field of the Earth, because technically the Earth is ground, right? It's like neutral, right? So it doesn't have a net electric field. That's a bit of a lie, but it's a good one. Magnetic field, though, on the other hand, right, definitely does exist. So by putting this magnet on a freely rotating base, what have we just invented? This is a compass, right? So compasses, right, were invented or thought about. Like, magnetism predates electricity by a long shot. Like, electricity we're playing around with like in the 1700s, right? Scientifically speaking. But scientifically speaking, magnetism goes all the way back to the BCE era, right? Ancient Greece and things like that. And they were using different like scientific models to try and explain what was going on. But they knew about magnetism a long time ago. The age of navigation and compasses would come a little bit later than that. But magnetism predates electricity by a long shot. So this magnet has aligned itself in the Earth's magnetic field. And so the red end of this, okay, this is where we find out how many of you are directionally challenged, right? Okay. Which way is this way? That's north. You go that way to get to Canada, right? Okay. What's this way? South. You go that way to get to actually the South Pole, because you won't run into Baja California if you go directly south, okay? Because California, Baja gets out of the way. Okay, and then, so which way is that way? East. Which way is that way? West. So which way is the red end of this compass pointing? It's backwards for you guys. Sorry. The red end is pointing that way. Let's see. White balance. Is there a way to flip my image? Nope. Okay, so what I will do is I will flip it in my head. Viewing angle. Nope, that wasn't an angle at all. That was a... yeah, there's no way to mirror the image. Okay, okay, I will do this. So the green end is pointing which way? Which way is this way? North, right? Okay, so what must the green end be? A north or a south? In order for it to point north, right, it has to be the south end of a magnet, okay? Well, this is going to mess up because of the mirror here, but you'll have to trust me, okay? I've got another magnet in my hand, right, okay? And I'm going to bring it, and let's see what happens. If I try to bring the red ends and the red ends together, what happens to the two red ends? It kind of gets out of the way, doesn't it? Okay? And then if I take a green, right, towards a red, now what happens? It's attracted, isn't it? Okay? So what do we know about the green and the red? They must be opposites, right? Okay, because opposites attract, okay? If I take away my bar magnet, okay, green points that way, but for me, in the correct orientation, the red is pointing that way. So we know that these two have to be opposites. Now, this one's labeled. So what is green? It's a south pole, okay? And the red then, therefore, is a north pole, right? Okay? So the green, right, is a south pole. The red is a north pole. And even though it's backwards for you guys, I just messed up the balance, okay? So the north on my Elmo is actually pointing that way, okay? So the north end of the compass is pointing towards which direction? The North Pole. Phoebe's giving up already, okay? And she should, because this got confusing all of a sudden. Which way does the north end of a compass point? It points north, right? But in order for the north end of a magnet to point north, what must be up there? A south magnetic pole? Okay, where does Santa Claus live? Okay, Santa Claus lives at the North Pole, right? All right. Where do penguins live? South Pole. I can't. Galapagos Islands. Whatever. All right. So penguins live at the South Pole. Santa Claus lives at the North Pole. We call the place where Santa Claus lives the North Pole. Why? Because the north end of a compass, which is a magnet, points that direction. So Santa Claus must live near the Earth's, fill in the blank, magnetic pole. South magnetic pole. So we call that direction north because the north end of a magnet points that way. But in order for the north end of a magnet to point that way, that direction must have a south magnetic pole. So penguins live at the South Pole. Why is it called the South Pole? Because the south end of a magnet points which way? That direction, right? The south end of my compass points that way. But for the south end of a magnet, a compass, to point that way, there must be a north magnetic pole down there. I'm greatly oversimplifying the location because the Earth's north magnetic pole is actually in the middle of the Atlantic Ocean, and the south magnetic pole is somewhere in Canada, which explains quite a lot. But the idea, right, that a magnet aligns itself in a magnetic field is the key of what we want to try and capture here. And I tried to blow your minds a little bit by telling you that the North is the South Pole and vice versa, right? It's still the North Pole. We still call it, and as a matter of fact, if you want to be really careful, you say it's the North Geographic Pole, okay? But magnetically speaking, Santa Claus lives near South Pole, okay? I'm not responsible, but don't look at me like that, okay? This isn't me. I'm just telling you the way it is, okay? But the bottom line rule for our magnets, right, is that they create fields in and of themselves. Compasses, other magnets that are freely floating, will follow the lines, the magnetic field lines that exist around those things. The Earth's magnetic field, right, okay, which they have done totally incorrectly on this picture. Look at, they put North Magnetic Pole and Geographic North Pole together. That's wrong, okay? Because the north direction, anyway, see, even Peter Reed got it wrong, okay? So, yeah, it's, magnetic fields can be confusing. All right, and what does the button say? What's the square root of -1? I, imaginary number. What's 2 cubed? 8. I'm not sorry. All right. So what do we know about magnetic fields? Okay, so magnetic fields, right? They have north and south, right? And the same thing, like opposites attract, likes repel. This is okay. Is there a magnetic field? Is there a pattern of forces that exists around a magnet? Will other magnets experience force? Yes, right? So there is a field there, and we've got to be able to kind of talk about that field. Like charges, back when we started, like very first day of this course, magnetism is an intrinsic aspect of the fabric of the cosmos. In other words, things have mass, they have charge, and they also have magnetism, little magnetic fields. If you take a bar magnet and you start cutting it in half, okay? So we start with something that's like, say we got a north and a south pole, and then we break this in two, right? Okay? What you don't end up with just a south pole and just a north pole. This thing will turn into two magnets. And if you cut it again, it'll just make two more magnets. And you can cut all the way down to the atoms. And individual atoms will have north and south poles. Okay? So it's fundamental, it's intrinsic, and is distinct from electric charges and electric fields, because unlike electric fields, magnetic fields don't have a start and a stop. Back up. Electric fields, where do they start? Positive charges. Where do they end? Negative charges. This doesn't happen with magnets. With magnetic fields, they are closed loops. They are circles or ovals or whatever shape, but they have no beginning and no end, like a circle, right? You can pick any point on a circle and get back to that point and close off the loop. So if we picture a magnetic field, let's say, of a bar magnet, okay? So I go here, I got a north, and I got a south. There are kind of some rules to kind of go along here. So by like sort of convention, this is just so that we can all agree and talk about the same thing. We say that magnetic fields come out of or flow away from north poles. So I can draw like a magnetic field coming out of a north pole, but it forms a closed loop. And so by extension, where does it go in? A south pole, right? So it comes around, okay, and we come in there. And I can draw arrows, right, on this thing. Now, a lot of times the drawings will stop here, okay? And I don't like these kinds of drawings like this because they are hiding something from you that's very important, that makes this distinct. Electric fields started and stopped, right? They started somewhere, they start on positive, ends on negative, definite beginning and end. But with magnetic fields, there's no start and stop. But I've drawn a picture that looks like it, right? And you'll look on the internet, and you'll look in a book, and you'll draw a picture like this and go, this is the way it is. What they didn't draw was the continuation of this field line through the magnet, okay? They form closed loops. So if I have a field that comes in to a south pole, well, it has to keep going, right? And then come out of the north and eventually circle around and come back on itself. Magnetic fields form closed loops, and they do it in three-dimensional space. So if I take my little magnet here and I hold it up, right, and my red end is the north end, right? The picture in my head that I have to think about is like a three-dimensional fountain, okay? Like a flowering of magnetic field as it comes out of the tip of this thing. And then those magnetic fields will turn around, come back, and get sucked up into the bottom, okay? And you can think of it as a flow or something like that. Same thing with the Earth's magnetic field, okay? The Earth's magnetic field comes out of the South Pole. Again, it's backwards, right? North magnetic pole is down there. So the field lines come out where the penguins are, and they come back down and they come in where Santa Claus lives. Right? But they pass through the Earth, continuing their full circle. and connectedness. So this is why it's very different from the electric field in that sense. Okay? All right. Let's see. What else? What else do we need to know? There is never a North Pole by itself. There's never a South Pole by itself. Those are, in physics, we call those magnetic monopoles, where like pole, polar, right? North and South Pole. Mono meaning singular, right? So they've been theoretically, like mathematically shown to be possible, but we've never measured one in nature. Nobody's been ever able to make one, okay, in a lab. So as far as we know, magnetic monopole is not a thing. You find one, you let me know, we get a Nobel Prize. All right, so all the other rules for fields we adopt from the electric field. So there were other rules, like electric field lines can't cross or tangle with each other, right? So that's why I drew these magnetic fields sort of kind of pushing away from each other. I could draw more on here and make it even more confusing, but we've got sort of the general idea. So no crossing or tangling, the density of lines, like where is this magnetic field strongest? Kind of like, you can think of like in the middle, like they're really close in here, right? Okay. But they're also really close right here. But as they get out here, it gets a lot weaker, doesn't it? Okay. So all of those similar concepts and ideas with our visualization of the field are true. Big difference, though, magnetic fields don't start and stop, right? They form closed loops. Fundamental physics. I'm about to go and draw a bunch of pictures where a magnetic field will look like this. The symbol, by the way, for magnetic field is capital B. We don't use M or capital M because that gets really confusing with mass. So we've adopted B, capital B, for the magnetic field. And you're looking at that going, well, Mr. Balogh, that field started and stopped, right? It looks like it started on the left and it stopped somewhere on the right, okay? But again, kind of like when we drew this with the electric field and we said there's an electric field everywhere in the page or something like that. It's coming from somewhere, it's going to somewhere, but I know at infinity it's going to loop back around on itself. So there are kind of these little caveats. And the easiest way to get a field that looks kind of like that one is to just put a north pole there of one magnet and a south pole right there, right? Because what do the field lines want to do? Where do they come out? North poles. Where do they go in? South pole. So if you put two magnets next to each other, this is what they'll do, right? But if you try to put a north and a north together, can I draw one that just goes across? No, right? Because I got stuff coming out here, I got stuff coming out here, and they'll have to bend away from each other, right? To get out of the way of each other, because they can't cross or tangle. Right? So just realize a lot of times we will simplify the drawing or the idea by saying I've got a nice straight magnetic field. That's like in a small region of space where we want to concentrate on what's going on. Okay? The field lines will continue on. They'll eventually form closed loops somewhere. But we often don't draw the whole magnetic field in place. So taking everything we just learned about magnetic fields, let's see if you can suss out a quiz. All right, so this is where it's going to get really funky. And I'd apologize for this, but I'm not responsible for how the universe is put together. We alluded to force, and I haven't really talked about force yet, so we're going to talk about force. Back up. There's something worse going on here. I had my little magnet on a stand, right? My compass, right? Okay. And when I brought the opposite side in, right, there's very obviously a force here, right? This force of attraction, okay? But what is this force causing to happen? What's the compass doing? It's rotating, What do you call a force that causes a rotation? A torque. How many of you have chosen to remember torque from Physics 2A? Okay, Truman, put your hand down. You don't want to admit to stuff like this. How bad was torque? Not that bad? Dr. Kerfoot must be a better teacher than, or Mr. Evans must be a better teacher than me. Torque is horrible. Okay? So what's really kind of happening down here, and we will talk about it a little bit, is that there are torques involved. But we're gonna ignore the fact that compasses rotate in fields for right now, and we're gonna really try to simplify and nail down what's going on when magnets feel forces. However, I can't talk about actual physical permanent magnets yet, because that's quantum mechanics. So we are now going to ignore actual physical magnets, bar magnets and refrigerator magnets, and we are going to talk about magnetic fields and charges and how charges respond to magnetic fields. Because if you put a charge in a magnetic field, it's going to deflect. And I'll try to demonstrate for that for you next Monday in lab, where I actually have the materials to do it. So I hate doing math first, but I really don't have much of a choice, okay? Because I just want to lay this on you and see where it takes us. When a charge moves, and in order for a charge to move, it has to have what? Direction and magnitude. What's that called? Velocity. Right? Some of the things we really blank out from 2A, don't we? Right? Okay. In order for a charge to move, it has to have velocity. So if a charge isn't moving, it's not going to feel this force. Okay? But the magnetic force on a moving charge in a magnetic field, okay, is going to be equal to the amount of charge that's on it, the velocity that it's moving at, the strength of the magnetic field. You know what? I made a boo-boo. Don't put a vector sign on it. Times the sine of the angle between the two things that are vectors in here that I can't write down as vectors yet. Exponents. No, it's Q times V times B sine theta. Your book does it this way. It says this is the definition of a field. It's a force divided by QV sine theta, and they'll put a absolute value sign. So those are the same equation, okay? Most websites and physics textbooks will do it the way I did it in the box, okay? But it's not wrong, right? We've just done a little bit of algebra there, right? To rewrite it the other way. This phenomenon where if you take a moving charge and you put it near a magnetic field and it experiences a force is what we use to kind of define the strength of a magnetic field. It's actually easier for us to do it this way than it is to get into all that torque business with rotating compasses. This happens in the Earth's magnetic field all the time. The Earth's magnetic field is responsible for shielding us from many of the charged particles that are coming from the sun. Technically, those charged particles form a type of radiation, and without the Earth's magnetic field, we would be exposed to the full brunt of the sun's radiation at our given orbital distance. Instead, the Earth's magnetic field, being a magnetic field, and that radiation being made up of charged particles, hydrogen and helium ions and electrons and other things, those charged particles get deflected. They get pushed away, and our magnetic field forms a type of force field, a shield, right, that protects us from those ionizing bits of radiation. Now, there's other forms of radiation that can get through and that cause sunburns. What kind of radiation is that? Ultraviolet light. Okay. Well, light doesn't have mass or charge, right? So it'll sail right through a magnetic field, not be deflected by it. Because this force, right? We need a charge, right? If you're neutral, no force will be experienced, right? Even if you're moving, even if there's a magnetic field there. So our Earth's magnetic field protects us from a lot of this ionizing radiation. However, charges, as an added bonus, not only will get deflected, they'll start to circulate around magnetic field lines. And then the north and south poles of the Earth become sort of collecting zones for those charged particles. And when those charged particles slam into the atmosphere, they cause the aurora borealis and the aurora australis, the northern and southern lights. So the northern lights, the southern lights, these are charged particles trapped in the Earth's magnetic field that are slamming into the atmosphere as they are drawn to the north and south poles of the Earth, okay? And because the field lines are coming out or going in, right, those charges are pulled into the atmosphere, and it sets the gases in the atmosphere to glowing. The nitrogen, the oxygen, they start to fluoresce a little bit. So anyway, we're talking about like very real physics that's taking place. But here, okay, so here's the problem. Let's talk units for just a second. What are the units of force? A Newton, right? What are the units of charge? Coulombs. What are the units of velocity? Meter per second. What are the units of theta? Trick question. It doesn't have units. Okay. Degrees or radians are not, they're just placeholders. They're not units. So what's a Newton per coulometer times second? I don't care anymore. Yes, thank you. It's a Tesla. Yeah, this is the units of magnetic field are Teslas. After Nikolai Tesla, a scientist and inventor who was a contemporary of Thomas Edison. Okay, Mr. Bailey, you don't have time to go into this. Short version is Thomas Edison's a jerk. A very bad man. Takes advantage of people, gets rich off of other people's work. Okay? Nikolai Tesla is probably a genius. He was also crazy. Okay? And Edison took advantage of him, and as did Westinghouse and some of the other robber barons of the time. But we honor Tesla by naming the magnetic field unit after him. Thomas Edison gets nothing, as he deserves. If you want to know more about how bad Thomas Edison was, just see Elon Musk. All right. Teslas, we got that. Okay. Now, there's another unit that floats around, okay, that you should just be aware of, okay? And that's the Gauss, okay? It takes 10,000 Gausses to equal 1 Tesla. And the only reason I mention that is because sometimes you hear about Gauss, especially in chemistry. Chemistry doesn't use the metric system. Well, they kind of do. They use something called the CGS system, centimeters, grams, seconds, which technically isn't the metric system because the metric system uses kilograms, meters, seconds. Anyway, they'll use Gauss. And a lot of times, if you look up the Earth's magnetic field, they'll tell it to you in Gauss. That's because the Earth's magnetic field is actually pretty tiny, okay? It's about half a Gauss, or 0.5 times 10 to the minus 4 Teslas. So even though Tesla is the actual unit, we move the exponents around sometimes with Gauss. And I wanted you to know, because if you're looking up things in tables or you're seeing somebody lecture on YouTube or something like that, and they just drop the word Gauss for the unit of magnetic field, just realize they're doing it slightly different. It's okay. It's not terribly wrong. We're just arguing about where to put the decimal point. Okay, so we've kind of covered the units a little bit. Seriously, just kind of give up. Don't try to break everything down and figure out all the units. If you put in your force in newtons and your charge in coulombs and your velocity in meters per second, you're guaranteed to get a Tesla out. Okay? Just don't mix up your units. Don't put in centimeters per second or miles per hour or anything in there. You'll be fine. All right. But force and velocity and magnetic field are all vector quantities, aren't they? And you'll notice I erased my vector bar over this thing, right? Because this is where this course gets really bad. The direction for all of these things, the direction of this force, depends on the direction that the velocity is pointed with respect to the direction that the magnetic field is pointed. So before, with electric fields, it was kind of easy, wasn't it? Right? We had, well, I dropped that casually, right? But electric field, like if an electric field's pointed to the right and I put a positive charge right here, what's it going to do? What direction will the force be on it? You guys already forgot. You took the test. You're done. If the electric field is going that way and I put a positive charge, which way will the force be on it? To the right, right? Positive charges follow the field, right? So straight up, just look at the field, we're done. You cannot do that with magnetic fields, okay? The force that charges feel when moving in magnetic fields is perpendicular to the velocity and the field at the same time. No, that didn't hit you the way that I expected it to. You should be crying in a puddle, right? Yeah, thank you. Okay, so let's see if I can't ram home the problem. Let's say that I have, I don't know, a magnetic field that's pointed to the right. Okay? What? I just got done letting all the light in. Did that help? Yeah, okay. All right. So let's say I've got a magnetic field that's pointed to the right. Like everywhere in the front of the room, I've got magnetic field pointed to the right. Okay? And then I come along and I say a particle, a positive charge, okay, is moving upwards. Okay? What direction is perpendicular to both of those directions at the same time? It has to be either out of the board or into the board. Right? We need something that's perpendicular to V. So that could be right or left, right? But the problem is right or left perpendicular to B? That's parallel to B, isn't it? Okay? And so I can't use right or left. But in and out is also perpendicular to V and simultaneously perpendicular to B. Now, that's a lot of like visualization, but you'll notice there's a big problem. For the first time, really, in all of physics 2A and 2B, we are being forced into what dimension? The third dimension. We've done a lot of work where we like say, well, it's three-dimensional, but we'll draw the two-dimensional picture and we'll just pretend. We did that all with electric fields, right? Either three-dimensional in space, all that kind of stuff, right? But we're just going to draw it in 2 dimensions and wink, wink, it works. And it does for the most part. But here we don't have a choice. The force that this charge would feel, okay, is either out of or into the board. And now we have a 50-50 chance, right, of getting this right or wrong. The way that we choose, the way that we define the direction of the force on a charge moving in a magnetic field is through something called the right-hand rule. Okay? So I want everybody to raise your right hand. We are calibrating right now. We're just making sure. Okay, repeat after me. That's not that kind of thing. Okay, I just wanted to make sure that you had your right hands, okay? There, you can put them down. There is a point in the next couple of weeks where you are going to be so confused that you will not even remember which hand is your right hand, okay? Yes. You're going to get so deep into this, and you're going to be in a problem, and you're going to be like questioning your life choices and all these kinds of things, and you will forget which hand is your right hand. Especially you right-handed dominant people. You are at a disadvantage here. Left-handed people, rejoice. For the first time in your lives, the scissors are going to be on the correct side. So, what do I mean by that? Right-handed dominant people are writing, right? And in order to do the right hand rule, it's in the name, what must you do with your writing implement? Put it down so you can do the right hand rule. I've watched students on exams, okay, all stressed, right? And they get to the right hand rule problem, and they're just writing, and they'll pull this hand out, and they'll do the thing, and then they'll keep going. And I have to go over to them, and I have to like kneel down in front of them to get their attention. I have to say, you just used your left hand. And they'll look at me like, what? Like, you just used your left hand. And they'll look at me like, no, I didn't. Yeah. Okay? So, I don't know. Get a tattoo. Use Post-it notes. Something. Right? One of the preeminent philosophers of our age, just master when it came to thinking. His name was Winnie the Pooh. Said this. He said, I have no trouble telling my right paw from my left paw. It's knowing which one to start with that makes all the difference. That's deep. Steve, you don't think about it. Just think about that for the rest of the day. No trouble telling the right from the left. It's knowing which one to start with that makes all. It's very wise, very deep. Okay, right hand. Okay, now you need to know that your book does this a different way than like pretty much every other book does, any other right hand rule. I'll follow your book's method, but I'm going to mess up a few times because I'm used to doing this another way. I also tell you that because if you are looking at videos or other resources, maybe you're talking to one of the tutors, okay, and they've taken 4B, they do the right hand rule slightly differently. It all works. It's all the same thing. It's just you'll start arguing over which finger and which part goes to which way, okay? I'm just letting you know this, okay? But in your book, okay, your book says you take your right hand, and I like to call it the handshake rule, okay, because you hold your hand like you're going to handshake with somebody. So flat palm, fingers extended, thumb pointing out to the side like that, okay? You take your thumb and you put it in the direction of the velocity. So in this example, everybody get your right hands out, right? Your thumb should be pointing up somehow, okay? If you're sitting there in the, like, right, your thumb should be pointing, and you can, like you can hold your hand pretty much any way you want and your thumb stays up, doesn't it? Okay? And then you are going to put your fingers, okay, in the direction of the magnetic field. So you see how I can rotate all the way around, and okay, if you are causing physical pain, like actual physical pain in your hand because you're doing the right hand rule, you're like, Mr. Man, I can't get it, it hurts so much. You're doing it wrong. Okay, there should be no physical pain. Mental and emotional stress, yes, but physical pain. So you can, like, my thumb's up, right? But I've got like basically 360 degrees where I can hold my hand, right? My fingers in any direction, right? So thumb up because the velocity's up. Magnetic field, my fingers line up in the magnetic field direction. Which way is your palm facing? Into the board, right? So this is called the definition, right, for the direction of the force. The right hand rule for the direction of the force. Thumb in the direction of the velocity, magnetic field in the direction of the fingers, and the force would then be directed in, right? It can be either in or out. Those are both mutually perpendicular directions, but we just choose and define with the right hand, right, what direction the force would be. So this charge would experience a force into the board. in the example that I have here. Okay. Let's do the opposite of this one. What happens if the velocity is going down? This is easy to change. Velocity is now down. Okay. How do you do the right-hand rule for this one? What does your thumb do? Goes down, right? Okay. And then your fingers, where do you put your fingers? Direction of the magnetic field, right? So which way is the force now? It's going to be out of the board. Okay? You're going to want to practice these a lot. Like get flashcards, quiz each other, do something. Yes? Don't. Oh, okay. Oh, it's so triggering. Don't use your left hand. Okay? Don't ever. Okay. There is, I really shouldn't say things like this. There is a left-hand rule. I strongly encourage you to ignore it. Your book doesn't talk about it, but you'll find some crazy weirdos on the internet that will talk about it. And they might have PhDs, okay? All of this has been defined from the point of view of a positive charge. What do negative charges do? The opposite. And so you might, left hand works. I know it works. I know it works. It's perfectly valid. But do you know how many times I've had to straighten out somebody's left and right hands if we teach the left hand rule? It's like all the time. Don't do it. Stick to one, the right hand rule. It's the realm of safety. Okay? The thing that you have to remember, we're going to use the same muscle we used in electric fields. If it's a negative charge, what do? Flip it. Right? So if this were an electron going down, right? I go my thumb down, my field fingers like this, right? Using my right hand, my palm is pointed out, and so the answer for the force, if it's a negative charge, would be in. That, for some reason, the majority of people have an easier time getting correct more consistently than if I start teaching a left-hand rule. So you will see left-hand rule mentioned in various places online. ChatGPT probably would bring it up because it's an idiot. We will not speak of it again. No such thing as the left-hand rule. Okay. How do you draw three-dimensional things on two-dimensional pieces of paper? No, not depth, not isometric view. Oh, please, no. My brain doesn't work that way. And it's actually very clumsy because unless you have a correct idea of scale, you're not going to get through it. So let me show you how we do it in physics. Okay, this is, again, just another tool to help you visualize what's going on. I want to draw. Okay, so let's do this. Let's do a velocity that's pointed to the right. But this time, I want the field to be going into the board. Okay? So ignore this picture up here. Okay? I've got velocity going to the side. Look at the screen up there, right? And in the plane of the screen, okay, there is magnetic field that is going in, right? Again, we have to live in 3 dimensions, right? So like, I can sit here with the right-hand rule. If I know the magnetic field is pointed into the screen, I can use my right hand. Let's figure out the direction of the force on this one, okay? So which way do you put your thumb? Start with the V, right? Your thumb is the V, right? So your thumb goes in the direction of the V, right? So my thumb goes to the right, as pictured in the screen, okay? What direction did I say the magnetic field was? Into the screen, right? So which way are you going to take your fingers? You're going to rotate your arm around, whatever, right? Okay, until your fingers point in and your thumb is pointing out. Okay, do we have an alignment now? Do we have the correct directions for the V and the B? Which way is your palm pointing? Up. The force on this charge is up. Okay, well, I can draw up. But how the heck do I communicate what the field was doing? Now, I guess you could say be in. Be in what? Be in class. Be in, I don't know, right? So what we do in physics is we think of the field as a set of vectors. They are vectors, and vectors ultimately are arrows, right? They have direction, okay? And like a archery arrow, if the arrow is headed away from you, what end of the arrow do you see? The tip or the feathers? And what do feathers look like? They look like X's. So we'll draw X's to indicate that the magnetic field is pointed into the screen. What happens if the magnetic field is pointed out of the screen? What if we have a V and we have a magnetic field now that instead of being pointed into the screen is coming out of the screen? This gets violent, but if I shoot you with an arrow, if the arrow's coming directly at you, what part do you see? You see the tip. So to talk about a field that's pointed out, we'll draw the dot, the tip of the arrow coming at you. A lot of times in books, they'll like draw a circle around these, right? They'll like circle the X's. Most people don't do that when they're just drawing things, right? It's a lot of pencil and a lot of time to go back and circle all those things, right? So just try to be careful about what you mean, okay? But if this were my drawing, right, and I've got my magnetic field pointed out, and I got my velocity, how do I do the right-hand rule? What do I start with? V. My thumb goes in the direction of V, right? And then I got to have my straight fingers. Don't bend your fingers at your knuckles, but flat palm, right? Okay. So V to the right, and now I've got to kind of move something in order to get this to work. I've got to come out of the screen, right? So V is to the right still. My magnetic field's coming out of the screen. Which way is my palm pointed? In this case, the force would be down. How's your brain? Yeah? Okay. Okay. All right. All right. Well, okay. A magnetic field, let's do up. A magnetic field is pointing up everywhere in this picture, okay? And the force that a positive charge feels is to the right. What direction is the velocity? We just practiced a bunch where you start with the velocity, but what if you don't know the velocity? Start with what you know. What do you know? Fingers. The B. Which way does the B point? Up, right? So we put it up, okay? And then with the B up, now we know something about the force. What direction was force, by the way? It was the palm direction, wasn't it? So which way do I want to face my palm? To the right, okay? Which way is your thumb pointed now? So you would draw the velocity. Oops, not dots. X's. All right. The velocity is up that direction, and the force is down that way. Which way is the magnetic field? What do you know? You know V, so get your thumb going in V, right? Just start there, wherever it is, okay? Yeah, don't hit each other there in the back. I'm watching, okay? Right? And then now you have to get your palm to go which way? That way. This is getting... And this is where you start, like you're sitting here going, okay, there should be no muscle strain when you're doing other than brain strain, right? Okay? But yes, sometimes you're sitting there, you go, you know what? Rotate. Okay? Okay, you can rotate your whole body if you need to, right? V, thumb, right? The F, so I've got V going that way, I've got F pointing down this way. Which way is the magnetic field pointed? Out of the screen. V would be, I could draw the dots everywhere, but I'm not going to do that. Okay? All right. Let's see. Give me a direction. Up, down, in, out, left, right. Left? An electron is moving to the left. Give me a up, down, or in, out. Out. In a magnetic field that points out of the page. What direction is the force on this electron? V is to the, that way. What is that way? Left? Okay. And the magnetic field is now pointed out. So the answer should be up, right? No. It was an electron.
Oh my god. The electron's opposite.
Yeah. You'd use the right-hand rule, and then you flip your answer, right? We use the right-hand rule to say that the force would be up, but it's a negative charge, and so it points down. But Mr. Bates on the left hand. We draw three-dimensional pictures on two-dimensional planes by using X's or dots to talk about something going into or out of the plane of the page, okay? It can get really confusing sometimes to talk about these directions, okay? So just to make sure that you understand that in physics we actually have like calibrated all of our directions, okay? What's this way? Right or left? Okay, that's right. So that means this side is left, okay? Which way is up? This is up and this is down. Okay? Which way is in? Into the screen. So which way is out? Well, it's out of the screen. It can be very easy for up and down and in and out to get confused. Where does up and down live? It's in the plane of the surface, right? Like an X and Y coordinate system, right? Okay? But in and out takes you away from the plane of the page. So if a problem says a magnetic field is pointed up in a region of space, the default way you are supposed to read that is that it goes which way? In the Y direction. Okay? That doesn't always happen in every problem and all that kind of stuff. Sometimes they'll say up. They'll get really bad. A magnetic field points up out of the page. And now you're like, so not everybody follows the convention, but just so you know. And generally, we call this north, south, east, west, and then there's no other direction for it. It's just in or out, right? Okay. So up and down without any other explanation attached to it means perpendicular to left and right, okay, in the plane of the page. Was there a hand? I thought I saw a question. No? All right. A lot of times you'll see this big master equation that relates. So to calculate the numbers, you use the thing in the box, right? Okay. But to get the direction, you use the right-hand rule because it is a vector. But a lot of times you will see this equation written as just Q times V times B. The angle that is sitting here, this sign of the angle, that's the angle between V and B. What's the angle? Whoa, where would it go? What's the angle between V and B in this picture? Which way is V? To the right. Which way is B? Out. Okay. What's the angle between right and out? 90 degrees. What's the sign of 90? 1. So you'll see QVB, right? And you're like, well, what happened to the angle? If you see QVB, you know that everything's at right angles to each other, okay? Now, the reason I bring this up is because you can have situations where, let's say the magnetic field is pointed like this, and the velocity is pointed like that. Do the right-hand rule for this one. Don't do that because you hurt yourself. Because you can't get your thumb and your... Remember, no physical pain, right? Okay, so your thumb and your fingers can't point in the same direction, right? Right? Okay. So what is the force here? It's 0. What's the angle between those two vectors? 0. What's the sign of 0? Okay. So yeah, if the velocity were pointed the other way, like magnetic field's to the right and the velocity's to the left, that's still 0 force. So in order for a charge that has velocity to feel a force from a magnetic field, what's required? There must be a component of the velocity that is perpendicular to the force. And if it's not 90 degrees and it's not 0, then you're kind of forced to, pun intended, figure out what the angle is, right? So just draw your pictures and you'll be all right. Okay, we did a lot of like definition and ideas and concepts. What we're going to do on Thursday is we're going to do a bunch of examples, calculations, working our way through. We're going to evolve this singular charge into a whole bunch of charges and talk about the force on currents in magnetic fields. And we're going to work our way towards inventing electric motors. I will see you on Thursday.